Okay, and so we're going to start the last talk of today. And so thank you very much to Joshua Gans for presenting here, who is a professor of economics at the University of Toronto. And so again, for a brief introduction, Joshua is, I think, an expert in lots of different areas of economics. I know at least market design also has some work in the blockchain space. But today is going to be talking about the economics of AI. So thank you very much for speaking.
All right, well, thank you very much for inviting me here. I am nowhere near CS. I mean, I study things that seem to overlap, but I don't have any expertise. I do economics, but there's a good group of economists who think that I don't do. It's not pure enough economics either. So, you know, we're just take that for what you will. I thought what I would do here, given the audience, is present a talk that would show you sort of what economists who are studying artificial intelligence are caring about and how they go about analyzing it. My suspicion is you'll find the model simplistic and surprising and maybe trivial, but I think that there's some merit in showing you where we are as an economics field, given some of the other directions that a lot of the economics CS crossover are heading in. So this paper here is co-authored with my Toronto colleague, Kevin Bryan, titled 95% accuracy is not all you need. It is a paper that we wrote ahead of a startup that we founded, All Day TA, which is AI teaching assistant, which is used at the Rotman School and another 100 schools elsewhere as well. But, you know, as we do these things, we like to have an economic framework behind it. And this is a paper out of that. So obviously, we're taking a play on the famous 2017 paper title. The 95% accuracy, 95% is an arbitrary number, but people sometimes say that if your AI, whatever it is, can be 95% accurate, that's great. Otherwise, not so great. But it's mainly a talk about how much does accuracy get you in terms of impacts that we care about, adoption, and then subsequently impacts on things like employment. So I've written several popular books on AI. We call them prediction machines now in economics because we cast everything in terms of cost rather than getting into the details. So AI reduces the cost of prediction in a statistical sense. And this came out of work with the Creative Destruction Lab, which has had an AI stream for the past 11 years that I've been heavily involved in terms of AI startups being mentored and developed. The context for all this are papers in economics that have been looking at the impact, for instance, in particular, most recently on generative AI, read large language models, basically, on different forms of work. There was one paper here that included them being in a call center and showed that these did increase productivity, but mostly for the, we'll call them less skilled, but less experienced call center workers, not so much for the more experienced ones. So it had a democratizing effect. And then there was a recent paper by one of the same authors, Canaries in a Coal Mine, that looked at the different events of OpenAI releasing ChatGPT and trying to correlate it with movements in different types of employment, depending on other measures of how AI exposed their industries were. And the headline case is that it was great for all AI exposed employment categories, bar one, younger people, recent college graduates. And so hence they weighed in on that and Canaries in a Coal Mine, but it's actually good news for most. But it's only a very early days in being able to tease this out. And people worry about what the whole of AI is going to do for employment in general. This has been a consistent theme throughout this. You know, and some of the reasons that people think about how it's going to impact on employment are You know, is it going to have an adverse effect, or is it the very fact that people are around that will find something for them to do? That is, the opportunity cost will be there. There are preference limits. Do we want a human to do certain things? I can imagine some categories of that in art, etc., but there's only so much art you can produce. And they're just a general moral limits. People are just not going to be happy trusting the machines, which is a constant bit of debate. You know, do we really want to be ruled by super intelligent AI, you know, over human leadership? And I have to admit my bias is, have you seen the human leadership? I'm willing to take a risk. So the way in which, you know, microeconomists like myself would look at the impact of AI is to distill it down and look at its impact, say, on decision making. So this is a way we split up a decision. A decision under uncertainty takes state action pairs and translates them into payoffs, and you choose the action that maximizes your expected payoff. AI allows you to get a better prediction of the state, and that's all it does. And if you get, it's like an improvement in the information that you have. And if you were able to understand how a prediction mapped into an action, as you would, for instance, with a self-driving car, you could automate that entire process. And so automation is something different from AI, which may be obvious to everybody here, but at least 10 years ago, and we still struggle to get that pushed throughout economics. But the important part is this part here, which we call judgment, which is basically always human supplied. So the only way in which, as we understand it currently, Rich Sutton may disagree, is that you get some understanding of the trade-offs involved in terms of choosing an action in given states, is by having some utility, payoff, loss function, etc. And that has to come from people, even if it's programmed into a robot or something like that. And why is that important? Is because judgment doesn't come for free. It comes from experience, it comes from introspection, it comes from a whole lot of things as well. And if you improve prediction, you actually improve the returns to judgment. So that's a more optimistic scenario for people. And the other part that we look at this in terms of an economics perspective is, and Steve Jobs articulated very well with the invention of the computer. He said, we invented the personal computer, we created a new kind of bicycle, a new man-machine partnership, a new generation of entrepreneurs. And he was actually referring, when he was talking about this, when it was the ripe old age of 20, articulating the vision for Apple, reflecting on this article in Scientific American that looked at the cost of transport versus the body weight of various animals here, salmon, all the way up to mice up the top there, cows over here, automobiles, people, and then people on a bicycle. People on a bicycle, extraordinarily efficient way of transporting around. And what does that tell you? That tells you that the bicycle basically amplifies what the person is doing. And so Apple was founded basically on the whole philosophical base that one principle is that there's something very special and very historically different that takes place when you have one computer and one person. And they've driven this throughout all their advertising since. Basically, he called them computers bicycles for the mind. Now, the reason why we're interested in that is because, you know, when you think about AI, one way is to conceive AI as a set of tools, tools that help people make decisions, and then now translating into other actions as well. And they're another kind of bicycle for the mind in that regard. One thing, by the way, about bicycles is they took a long time to evolve. The first bicycle was 1817. By the time they started looking something that we recognize as or that would be able to ride as a bicycle today, it was a good half a century, and then so on. So that took a while, despite understanding it. In terms of things, this is coming up, and I'm sure you've been a party at parts at university. Nowhere more than in a business school, people worried about we have to AI prepare our students. And Ethan Mollick, who's done a lot of examination of these things, it says everybody wants to teach AI skills, but nobody knows what they are. And this is the whole thing. I sit in meetings and we must teach AI skills. And I'm like, what are they? Has anyone done any research on this? Has anyone worked any of this out? There's very, very limited knowledge of what it takes to work with AI. Why? Because we've literally just discovered it. And near as I can tell, there's a whole fields of machine learning working around, and basically their whole thing is to take an LLM and shock it like they would an animal in a lab and see if it's willing to kill them or not, or something like that. So we're still kind of exploring this, let alone being able to prepare our students for anything going on. So this is of concern. And some of the studies are a bit underwhelming. Some of the studies say where this is one of radiologists, which has a long history. I was in the room where Jeff Hinton said we should stop training radiologists right now, almost a decade ago. But the issue with the radiologists is when you give a radiological task to a human, good, to an AI, good, combine the two, terrible. And why? Because the humans overrule the AI at just the wrong time. In other words, they don't know how to work with it yet, is what's going on. So this brings us back to 95% accuracy. Is it going to be worthwhile? We're putting a lot of effort into improving the accuracy of AI in all manner of dimensions. That's basically, billions of dollars in some sense are being spent on this. It would be useful to understand if that's worth it. Okay, and so that's an economics question. So our basic question in this paper is, on economic grounds, what makes generative AI models unique? So we're going to look at those in particular. AI gives predictions, just like human effort or traditional statistical models, but there's also some domains where they're more accurate at given costs than in others. And so why isn't it used everywhere? This is a sort of a discussion that we've had since AI. Why has the adoption been so slow, especially with some real areas where it has been vastly superior? Obviously, driving being a great example of it. So the key insights that we're going to show is that AI does not need to be used by itself. It's used because it's bicycle mind in conjunction with other activities people are doing. And so you have to take that into account. And there's a difference between accuracy and knowing what problems for what your model will be accurate. Okay, so you have to understand what the properties of the model are in order to apply and use them. So just to take a motivating anecdote, consider 3 ways to drive a car. We'll consider 3 ways to drive a car. 70% of the driving is on a highway, 30% is urban. You might have a self-driving system that makes correct decisions 95% of the time, but it's difficult to know which 5% it's going to make a bad decision, and those can be kind of consequential. You could have a free cruise control system, we've had that for decades, that drives perfectly on highways but can't switch lanes, etc. So it's 70% accurate, far less accurate. But you kind of know it's on a highway and what its functionality is. And a human can drive 99% accurately on both highways and cities, but at a high effort cost. We have to pay attention, okay? So which should you use? Which should you use in these systems when you've got all these different things? And so understanding that is going to help us understand when AI can be deployed for economic decisions. Why are these more accurate AI systems not deployed, even when humans and other models are less accurate on some objective test? When should AI be used autonomously, that is without any of these human inputs, just let on its own, versus with human, we're going to call it verification. And I'll explain that in a minute. That's a nice term that also has a blockchain relation, but we're not going to get to that. Why do statistical procedures outperform, we'll call it generative AI, despite having lower accuracy? And what determines the economic value of an AI prediction system, and other things one might do with it? So here's what we find. So high accuracy alone is often insufficient for autonomous AI use. There are many economically important problems where verification costs and error costs matter much more than raw accuracy. And verification is going to be something that comes from people. And when verification is expensive and errors are costly, AI may not be used at all, even when it's dirt cheap and highly accurate. So the key insights is knowing when you don't know is more valuable than higher average accuracy for many, many tasks. In other words, we've got stuff to learn. Different employment patterns are going to be optimal for different problems, such as adversarial settings, O-ring problems, that relates to the space shuttle and weakest link, etc. Okay. There's been some prior work on all of this. Let me go less into that, since none of you have read the prior work, and why would you care? So let me go straight into the model itself. Because the model is very simple, much more simple than Tim's even that was going on that people queried. Okay, so we'll imagine a world. So it's going to be of a single decision environment. In that decision environment, there's n states, possible states of the world. We'll call it theta being the true state. And the probability of each is uniform, 1 over n. The decision maker has to choose out of n actions. That's no coincidence. N actions, or take an outside option. There's one action that is optimal. For a given state of the world, one of those actions is optimal. And that's it's a one-for-one bijection. So the payoffs are, if you match the action with the right state, the right number, the number of the action with the right number of the state, you get H. If you don't, you get L. H is positive, L is negative. The outside option yields a payoff of 0. So H is your reward for a correct classification, L is the penalty for misclassification, and H minus L represents the stakes, essentially, the difference between correct and incorrect choices. Where do these H's and L's come from? We're taking them as given, but I just want to keep you in the back of mind, someone had to come up with these things. It's coming out of the nature of the problem involved, which is invariably impacting on something people care about. Okay. What are the tools for decision making? We've got 3 broad ones that we're going to talk about above just winging it, guessing, just taking a random action and hoping for the best, okay? So there are 3 types of tools. First is the human one, verification. You can go and for each particular state, you can say, is this correct? Cost you C. Is this correct? Cost you C. You keep going until you find, yes, it's the one correct state. And remember, we've got a situation here where you've lost your keys. You know where they are, but you don't know where they are. So you know you're going to find your keys eventually, but you don't know which one it is. And so you can verify these these states, but only sequentially until you find the right one. That's your first thing. Very brute force, kind of what you have to do if you're before any sort of technology. Second, statistical method. It costs CS to run the statistical method, but you can run it over the whole space. And what it does, with probability P, it tells you, aha, I know what it is. This is the state. Great, you know exactly what action to take. With probability 1 minus P, it says, I don't know. In which case you are no better off. You've got no information, right? So it's deterministic. So running it multiple times will always give you the same result. So you only have to run it once. So it's a statistical method. That could be a form of AI, of course. We could, I'm not going to call it old-fashioned AI. That's too far ago. What's the term are we going to use for AI between 2012 and 2017? That great period when I wrote one book. We've got AI, which is more like generative AI that we're thinking, and it costs CA to run, and it returns a guess. It definitely says it is to the right state, and that is correct with probability Q, and with probability 1 minus Q is incorrect. And we're going to assume Q is greater than P, so the AI has got some legs here. it's black box nature. So you don't know which states it's going to correct wrong. You don't know how reliable it is. It's deterministic again. But the important thing is you're always getting a prediction from this type of AI, and you've got to decide whether it's still uncertain whether the AI is correct or not. With statistics, you know.
The correctness probability Q, you're saying the only guarantee you have is ex ante probability.
That's it. That is correct.
For some states, it could be wrong all the time. For some states, it could be right all the time.
Right. Oh, well, obviously, there's a ground truth that must be the case for that, but you don't know that because you don't know which state is the true one. So whatever the AI is telling you, there's no bias in it. It's just sometimes completely right and sometimes completely wrong. But it's not going to give you a signal like statistics would that it just really doesn't know. It's equally confident. Yes, I know the answer. The same thing as Adam Kalai is going to talk about in a couple of days. This issue of hallucinations. Basically, a lot of it is the AI trying to give you an answer with confidence without actually being confident themselves or being anything close to what we regard as confident. And so, that's an accurate description of some generative AI going on today. There's still a big issue of this I don't know issue and getting generative, how do you get them to do it? That's another thing. But at the moment, we're going to assume that isn't the case because we're trying to understand why the models now aren't being used. Okay. And so you can map this into all sorts of things like medical diagnosis, autonomous driving, manufacturing, fault diagnosis, HR, cybersecurity. All these parameters would act, sort of map into some version of that. But let me not spend too much time on that. So we're going to assume that the AI is actually more accurate than the statistic method. We like AI. It just doesn't have the known failure boundaries. The statistic method, its boundaries. It gives a correct answer or explicitly says, I don't know. So you can read this as, what would be the returns to getting something closer to the statistical thing than the generative AI, sort of a reverse question. All methods have their costs. The costs CA, CS, and C might differ. The error costs may be very, very large in critical applications, such as driving in certain areas. And the decision-making is going to choose a tool or mix of tools to maximize their ex-ante payoff. So they're going to have an actual strategy. So we're not just doing one or the other, we're combining some of these things. And so we're going to solve for this by comparing the expected payoffs across all possible combinations of the tools. Well, that's actually, we got three tools plus guessing and doing nothing. That can blow up quite quickly. So let's see if we can slim it down a bit. The first thing we can do is we can characterize the verification costs if we had no technological help at all. The verification costs can be solved quite readily. You take the random position of the true state in random ordering. If it's less than n, we verify exactly x times. If x equals n, we actually only verify n minus 1 times because we know if the second to last thing we've checked doesn't have the keys, the last one does. And then we calculate the expected value based on there and we simplify it and we get that nice little formula there, which is the expected number of verifications. Why is that important? Because beta times C is going to be your expected cost of finding your keys, okay? The other thing we can do is we can simplify the strategy space. If it's optimal to verify states when there are m remaining candidates, if there are m minus 1 fewer candidates, in other words, you found one and it didn't have your keys in it, it remains optimal to do so. In other words, the option value of searching more states increases as you whittle them down. Finally, and this is the important one that really helps us a lot, is it turns out you'd never want to run a statistical procedure after AI. Why? It's dominated by running a statistical procedure before AI. Because if you run a statistical procedure, the big benefit of it is you find out the state or you don't. That's not much, that's really, really valuable when you've got other ways to then think about that might be costly. It will save you those costs if it works. If you do it later on, Okay, you've already verified sequentially, or no, importantly, you've already run AI. You run AI, you're no worse. Your statistical test is less accurate at that point, so you would never use it. So the only point to use it is because it's going to sort out the problem for you. So you always do statistics first before AI, which means that we only have these many strategies to look at. Taking the outside off and guessing, verifying the basic ones, things with a statistical test first, things with AI first, not having to worry about the statistical test going second, and then all three combined. Each of these have, easy to calculate expected values associated with, and now all I'm going to do is compare them, right? So one key result we want to do is when you never use any AI at all. You've got this more accurate AI than everything else. You agreed upon that. When would you not use it at all? You won't use it at all when the cost of verification and the error loss is very, very, very large. Why the error loss? Well, obviously AI is sometimes giving you the wrong thing. So a big loss of error is a problem for all these procedures in some sense, but worse for AI because it's just kind of like, it's a better guess, right? But the verification cost is important because the verification is what you use in conjunction with the AI. You can get, for instance, the AI tells you it's this state, you can then go and check if the AI is correct. But if the verification cost is very high, you're back to guessing. Okay, so those two things. So technically, even as Q, which is the quality of the AI, goes to 1, and C, the cost of the AI, goes to 0, if these other costs are large enough and the stakes are big enough, you might not do it. Obviously, some of these things might get very small in that instance because this boundary depends on Q. Okay. So when is AI not used alone? So assuming some AI-based strategy is optimal, when is it a good idea to use it with other things? So obviously it's great to use it with verification when it's cheap enough because you get something from the AI and then you check it. And then if that doesn't work, you do something else, maybe guess. Or statistical pre-screening is sufficiently cost-effective. If statistics is good, you run that first to see if you should even bother using the AI. I kind of wonder if that's like a version of the GPT auto function going on. You give it a thing and it's a prompt and it's trying to make a statistical test about whether AI is going to be useful and it needs to do harder AI or easier AI. That's something that came after we conceived of this paper, so I don't know. So the key insight is even highly accurate AI is typically used with verification or pre-screening when errors are costly. And so the cost of verification comes up in both those things. Cost of verification, something that doesn't have to do with AI, has a big impact on whether you want to use AI or not. Oops, and there's a spelling. I didn't run this through GPT before I gave it to you, automatus. And so we can plug into the model fairly simple examples here. Actually, I'm not gonna worry about that right now. Okay, so let me just go through in the little time I get there. What would we do? What will we do with this model? So it's got some insights. How do we extend it to give it more nuance? And it turns out there's a bunch of things that we can do by tweaking the model in very small ways that I think give some insights. The first is to think of adversarial environments. Suppose there's an adversary who with probability lambda, a different lambda than the one we saw before, choose the state after the AI or statistical prediction. In other words, you're using AI and before it comes back to you, someone can actually just choose the state in a malicious way. Okay, so in other words, that's an extra layer of unreliability, and it might be done contingent on what the AI or statistical procedure is saying. So the expected payoff of an AI-only strategy decreases now if it's the same at lambda equals 0, but at lambda equals 1, it's all loss and cost because basically you can be manipulated into making a bad choice every single time. okay? So you wouldn't, that is a problem. The payoff to the statistical method decreases from pH minus S to 1 minus lambda pH minus S. In other words, it becomes slightly less unreliable, slightly less reliable, but not wholly unreliable. And you still don't have the risk of taking an action that's a loss, because remember, you're only going to take an action if you got the clear result from the statistical prediction. That just probabilities drop down. And so there's a threshold for lambda such that AI maxing alone models are dominated by statistical models. In other words, AIs are more vulnerable to adversarial attacks of this nation than statistical models. That is actually, one of the reasons we use statistics in like mechanism design, essentially, and all these sort of things, is this property, but it's kind of like interesting to explore it in this in this different setting. So you could have if you have a hacker penetrating a server, the state is the attack vector for it. You can keep the server up for good uses, for attacks, or take the server down. The worst an adversary can do with a statistical model is say, I'm not sure what's going on here. They can just gum it up, so you just don't know. Okay, but you can still optimize and get zero in that situation and avoid the worst. But the worst they can do with AI is choose an AI where the AI choose a state where the AI said, this is fine, you keep it up and you're attacked, okay? So in other words, there's a sense in which AI is more vulnerable, but remember why it's more vulnerable. It's more vulnerable because we're insisting on a sort of signal coming from the AI, and we're not sort of truncating it in interesting ways. Again, exactly like what we've got going in generative AI. This is why, for instance, people are putting into their scientific papers, please give me a favorable response, or this paper is terrific, etc. In some sort of footnote. And why? Because they think a referee is going to use AI rather than actually do verification in this instance to check on it, and therefore it'll get a more predisposed thing. That's exactly the sort of thing that we have in mind, right? And so that's a problem. That's a problem for the use of AI. That's one of the reasons why it's holding it up. O-ring tasks. What if you have lots of tasks? And we call O-ring. O-ring is after the failure of the ring on the one of the boosters on the Space Shuttle Challenger that caused it to explode. The idea being, if there's a component that's critical and it fails, the whole thing goes up. So imagine we've got M-sequential tasks, and where one error causes the entire process to fail. Then we have, when we use AI and guessing combined, we have, just following the AI, you have QM, Q to the power of M, as the probability of getting the right thing, getting the AI being right, Q to the, will probably QM, and 1 minus QM, you fail. Obviously, that's going to be highly skewed as you do more and more tasks. The Q is going to amplify out. And similarly, you're running those tasks M times, so you've got the costs of that. So as M goes to infinity, QM goes to 0. This is terrible use case for AI. And basically, for any accuracy Q less than 1, there exists an M star beyond which autonomous AI is suboptimal. In other words, if we're trying to chain a whole lot of things together, the more we're trying to change, the more likely it is we won't get to the endpoint that we want when you've got these critical tasks. Which again, as I run ChatGPT agent to do a mathematical proof on my behalf, and I watch it, and suddenly it's surfing the internet to look at iPod Air prices, AirPod prices. I wonder, is it really so? Now, unfortunately, it usually comes back, so there's some other stuff, but what other things are not happening with some of these processes? And I suspect this is the reason we do not have the multi-day AI runs that we know are going on in the AI labs, is because just too often they don't get to the right thing. And this cost, MCA, is just astronomical for the quality you're getting out. How they're going to solve it, I don't know, but we suggest, maybe some more statistics will work. What statistics? Who knows? Okay, What about self-correcting AI related to this problem? Suppose you have this autonomous chain of thought AI, and it's got the ability to express some uncertainty for a fraction of the inputs, gamma. Apparently, gamma and lambda are variables of choice this afternoon. It's like Sesame Street. Today's symposium is brought to you by the letters gamma and lambda. Well, there was an alpha. Yeah, we had an alpha, and then I changed it to A. It's aesthetics. I don't know. I like alpha. Alpha is like equity value. We use alpha. We're big alpha fans. But not here. No, we didn't end up in alpha. Anyway, fraction. Maybe I'll change it to a fraction of alpha inputs just to celebrate diversity. in diversity in notation. I actually have a whole paper, by the way, that I got published where I used emojis as notation. Because why not? One was, it was for the positive response was thumbs up and the negative response was thumbs down throughout the paper. You can see that in strategy science. Okay, sorry, that's a digression. Uncertainty for a fraction of, you can express uncertainty for a fraction of gamma inputs, and you can have improved accuracy on the remaining 1 minus gamma inputs. So we're going to tilt the thing. So in other words, some of it you can say, no, I don't know. Some of it you say, you give an answer, but you've applied something that is actually more accurate in those domains, but there's worse overall accuracy. So in other words, 1 minus gamma times QS is more or less than Q. Okay, so we've applied maybe some other process to sort this out, but it's reduced accuracy. Chain of thought AI dominates the sort of standard AI where you don't do this if this condition holds, okay? Which simplifies to gamma being less than a certain amount. So in other words, to gamma being less than a certain amount. So if gamma is that doesn't sound right. I have to go and check that. I'm thinking my logic's gone off. Never mind, just because I've lost at this point. But one thing we did find also, if human verification costs are low, you always prefer the strictly more accurate AI. So you'd prefer the chain of thought AI if you could check the results before you send it out into the world. Okay. Finally, second final, committee decision making. Imagine you have M people voting on something. They each get their own AI prediction. They can verify it if they want at a cost of C, and majority rule determines acceptance. There's 2 possible equilibria that arise. No one verifies, in which case, the AI guess is always adopted and you get whatever that payoff is. Or you get exactly enough verifiers in the majority, and you get a pivot type result, which only exists if the cost of verification are low enough. Relative to the accuracy and the losses. Otherwise, basically, you don't get this equilibrium because free riding, the problem is you'd like other people to verify, not you. And so that could happen. This might be something that might run akin to mixing blockchain with AI, I suspect, with exactly the sort of things. So the multi-agent settings create these free riding problems of verification. Remember, verification and its effectiveness is a complement to getting AI to be used and trusted. Okay. You could have a situation of limited liability where, yes, you could have a loss, so you're a doctor making a recommendation, a patient gets radiation therapy or not, you will invariably, there's a concern that doctors overprescribe these sorts of things. Why? Because they're not feeling the whole loss associated with it. Well, in that case, we know that the loss itself only appears in the payoff function for guessing, statistics plus guessing, AI plus guessing, and all 3 all together. So unless the AI is so ineffective that random guessing is optimal, limited liability makes AI strictly and uniquely more likely to be inefficiently used. Okay, so basically because the loss function is occurring in these AI things and not others, if we insulate the decision maker who's choosing the tools from those losses, they'll over-choose AI. Competition, you could have competition with predictions. You might have 2 agents involved in winner-take-all competition, access to a common free AI prediction. Each agent receives a payoff of 8 if they uniquely choose the correct state. If they both choose the correct state, they don't get anything. They get a payoff of L if they choose it incorrectly, which could happen whether they do it uniquely or not. So it's a competitive situation. You want to be the only one choosing the correct state, and you've both got this AI prediction. When does this AI prediction have negative expected value? It's free. So when does it worse than doing nothing? There's an asymmetric equilibrium where exactly only one agent verifies and the other takes their own outside option. And this occurs when QH is greater than C, that is, the verification cost is low enough. This is a common thing that happens. You basically got a coordination game. Some would have heard of Battle of the Sexes. That's what this game turns into, but it hinges on, the equilibrium hinges on the verification costs. And then you get these asymmetric equilibria. So verification creates a strategic advantage only when it enables uniquely correct actions. And if it's too high a cost, it will not do so. So there's lots of implications of this for practice in the last, oh, my watch. My watch is different from that. Is that synchronous? It's not synchronized to the, it's so electronic-y. Why isn't it synchronized to the something? Anyway, all right, that's fine. Oh, that's it. It's fine. Something's, this is a signal problem. It's definitive on the time, but it's inaccurate. Now what do we do? Okay, we need to go out and verify with a sundial. Okay, so implications for practice. So the AI benchmarks are a problem. We're worried about AI benchmarks in economics. Most of these benchmarks are based on getting an AI and letting it run, win a gold medal in the Olympics without any human intervention involved in that. Well, that's kind of silly. If people are not adopting AI because of this, they don't know what they don't know, then what we need to do is to work out some benchmarks about how AI works with people in some domain. Now, that's more costly to do than just running it on a computer, but there's something amiss here. AI integration is a system. Organizations don't adopt them autonomously. And so there's a problem when AI is used in conjunction with other tools. And this is an open area. And this is especially true on what we call the jagged frontier, which is basically AI is good at some things, not good at other things. But if you don't know what they are, that's a real issue. Okay. And then finally, we have incentive alignment issues, which is an active area of research. Human verification is part of the optimal system. It's costly, so the incentives for the human are going to matter for the usefulness of the AI. Again, we develop AI trying to remove the humans just because we can't trust them to do anything. This is a problem if that's not going to lead to adoption. So in the conclusion, AI's economic value is going to depend how it's used alongside other methods. High accuracy is often insufficient for many economically important problems, which may well be why we don't see the adoption we expect to. Verification costs and error costs critically determine optimal AI deployment, and verification costs are something that we either need to learn or we need to have other tools to reduce the cost of, etc. So knowing when you don't know is often more valuable. Different problem classes are going to require different deployment patterns, and empirical work is surely going to have to focus on this, certainly in economics. I have a book. If anyone's interested in the economic side of things, I tried circa a year ago to summarize where economics was on the microeconomics of artificial intelligence. Circa a year ago, that is prior to reasoning models. And not that I didn't think that models were getting better, but those models are kind of interesting on other dimensions. But nonetheless, there's stuff here. As I mentioned, we got a startup that was founded on the basis this paper led to, All Day TA. The idea being very much so, how do we, if we want our students to use AI, the big problem, we have lots of problems. We have problems with them using ChatGPT because they can do it well and do assignments. But we also have problems with them using ChatGPT because they do not learn what we teach. What we teach is often not in the data of ChatGPT or not the likely response returning. So, our model is that we're going to provide an AI teaching assistant that is exclusively and ruthlessly giving answers based on the data a professor provides, and is more than willing to say that doesn't seem like it's related to the course. Can you think again, to the students? In other words, not returning an answer. And then also in the domains of verification, providing inputs to the professors about what the answers are being given. And if the professor invariably realizes they've been unclear, they can, with a click, change the answer to a whole class of problems and clarify what they mean. So human in the loop. And this works because when students are asking the TA, the stakes are not too high. And it is possible for us in the background to verify what's going on. And that's it.